How does a standard round cellular building block transform into a microscopic swimming torpedo packed with DNA? The answer is a continuous 60 to 64-day manufacturing cycle called spermatogenesis. This biological assembly line powers up at puberty and keeps running seamlessly well into old age. This cross-section shows us exactly where that manufacturing happens. These circular structures labeled S are the seminiferous tubules inside the testis, and they act as the primary factory floor. Down at the outer edges of these tubules sits our raw material, a primordial germ cell known as the spermatogonium. This starting cell is diploid. That means it carries a full human genetic payload of exactly 46 chromosomes, which we represent mathematically as 2n. Keeping that diploid 2n starting point in mind is critical. The entire objective of the upcoming process is to perfectly have that genetic payload, so the cell can eventually fuse with an egg, all without compromising the cell's integrity. Looking at this flowchart, we can track the exact stages of cellular division. In stage 1, called proliferation, the starting spermatogonium divides via basic mitosis. It is simply multiplying its numbers into identical daughter cells, so the chromosome count stays completely intact at 46. During stage 2, growth, those daughter cells simply swell in size to become what we call primary spermatocytes. Notice the label still says 2n. No genetic material has been reduced yet. The major genetic shift happens here in stage 3, maturation. The primary spermatocyte undergoes its first meiotic division, meiosis I. It splits into 2 secondary spermatocytes, and this is the exact moment the math drops. The cell goes from 46 chromosomes down to 23, marked on the chart as N. To finish maturation, those secondary spermatocytes go through meiosis II. They divide one last time, resulting in the bottom row of cells called spermatids, holding steady at that half-capacity N chromosome count. Take a second to trace the lines from top to bottom. You can see that a single primary spermatocyte ultimately yields exactly 4 spermatids, each carrying precisely half the original genetic load. The genetic division is officially complete. But there is a mechanical problem. These spermatids are completely round and lack the motility required to travel towards an egg. They need a severe physical overhaul. This series of drawings illustrates stage 4, known specifically as spermiogenesis. It is crucial to distinguish this from the broader spermatogenesis process. In spermiogenesis, there is 0 cell division. It is a strictly physical remodeling from a round cell into an elongated sperm. First, the cell prepares the payload and the drill bit. The nuclear material condenses tightly, shifting to one pole of the cell. At the same time, the Golgi apparatus flattens out to form the acrosomal cap, which wraps over the anterior half of the nucleus. Next comes the propulsion system. The cell's 2 centrioles align, and the posterior centriole extends outward, pushing through to form the axial filament, essentially the propeller shaft. To power that propeller, the cell's mitochondria migrate. They wrap themselves into a dense helical sheath right around the middle piece of the axial filament. Finally, to reach maximum swimming speed, the cell sheds almost all of its excess residual cytoplasm. It strips down to just the essential organelles enclosed in a tight membrane. By discarding that dead weight and streamlining its internal anatomy, the stationary spermatid successfully transforms into a fully functional, highly motile spermatozoa. This diagram shows the finished cell, measuring roughly 60 microns in length. Its anatomy is highly specialized: a head containing the acrosome and nucleus, a narrow neck housing the centriole, a body packed with mitochondria, and a long tail made of the axial filament. Outside the body, these specialized cells operate on a strict timer. They remain viable and capable of fertilization for only about 2 days post-ejaculation, relying entirely on an alkaline, fructose-rich seminal fluid for energy and survival. Clinical male fertility is measured against these standard baselines. We test for oligospermia, which is an abnormally low count, or azoospermia, meaning a complete absence of sperm. We also look out for necrospermia, dead cells in the ejaculate, and verify that structural abnormalities like giant or dual-headed sperm remain below a 20% threshold. True fertility requires the entire 60-day assembly line to execute without error. Adequate cell counts depend entirely on a healthy early proliferation stage, while swimming speed and egg penetration rely completely on the precise physical remodeling of spermiogenesis. Here is your final roadmap to map out the entire process. Feel free to take a screenshot. On the left, you have the genetic math, halving from 2n down to n. On the right, the physical transformation, from a round spermatid to a streamlined cell. Ultimately, spermatogenesis requires a biological system to perform two massively complex tasks at once: a precise mathematical reduction of DNA paired with extreme structural engineering.